Welcome back. So far, we have discussed that the Scottish physicist Maxwell and the German physicist, actually, that the Boltzmann, they have brought out the speed distribution function for an ideal gas where large number of molecules are considered under investigation, and they have brought out that in the speed range of, if let's say v and a small increment v plus dv, how could the speed distribution functions looks like. It was looking like something we have brought out. This is that the psi c, you can see here that this psi c equation 1.13 in this PDF, you can see that psi c, that is the speed distribution function, is equal to 4 pi c square, where c square is nothing but the speed of the molecules, and in the bracket m by 2 pi kt and the power 3 by 2 and then exponential function e to the power minus m by 2 kt into c square. And we have plotted this speed distribution function by seeing that it is dependent upon the velocity, the speed, the mass, and the temperature. Mass of the molecule, temperature of the gas, and the speed of the molecules. Okay. Now, this distribution function is valid in a small range where the speed is ranging from c to c plus dc, and then we have plotted it with respect to temperature. That is, we essentially tried to see that how the speed distribution function for these molecules is behaving when the temperature is varied, as well as when the mass of the molecule, or essentially we can say the molecular weight of the gas, is varying. And we have seen the speed distribution functions distribution with respect to the molecular speed, something like what I have shown here, figure 1.1. You can see here the effect of temperature on the Maxwell-Boltzmann distribution for a certain gas. You can see here that there are three graphs, one a black line, and there are two distribution. We are showing it plots. We are showing that it's with a dotted line, and we have seen it that Ta, Tb, and Tc is the temperature variation, where the temperature Tc is more than Tb, and which is essentially in turn more than Ta. What we have observed that for the same constant number of molecules, if we are discussing that is in a fraction of molecules, we are having essentially same for all three graphs. What we are observing that at lower temperature the speed distribution has the lesser range, that is, the molecules are moving at a lesser velocity. Secondly, as soon as we are increasing the temperature, the speed distribution function is extended, and then this means the molecular speed goes higher. And then further, if we are increasing the temperature again to Tc, then it is more flatter, the curve. That means the speed distribution, or the range of the speed distribution, essentially increases. In turn, if we see again the effect of the molecular weight, or that is the mass of the molecule on the speed distribution function, again you can see in figure 1.2, I have written it here, dependence of Maxwell-Boltzmann distribution on the molecular mass. Now, you can see here we are taking the sample gases, let's say oxygen, which in the last talk I have shown that this is the molecular weight of 32, then 28, and then H2O, and then He, helium, and H2. We can note that the O2 in comparison to H2 is very high molecular weight. And then what we see essentially that the speed distribution of heavier gases are having a less range than the lighter gases. It can be understood in the different words that if for the same constant number of molecules, if we are observing, which is making that the area covered under each of these curves are essentially same, then the lighter gases are having higher molecular speeds than the heavier gases. This is having a very important application in terms of the aerospace sciences. What we see that we know this thing that the lighter gases are always found in the upper layer of atmosphere. This is the reason that because the lighter gases are having the more molecular speed, they reach up to very high level in the atmosphere, which is approximately termed as from sea level up to 100 kilometer above the sea level. Now, using this distribution function, Maxwell-Boltzmann distribution, we can essentially see that the molecular speeds, how to derive that. In kinetic theory of gases, there are three important molecular speeds which we talk about. They are root mean square speed, the average speed, as well as the most probable speed. However, in calculating the speed of these a fraction of the molecules, please note that from Avogadro has told that a 1 mole of gas has 6.023 into 10 to the power 23 molecules, which is a considerable number. Therefore, for each molecule to, to, to derive the speed, it is very almost very clumsy or almost impossible task. That's why this distribution function for a fraction of molecules tells that between a small range, let's say C plus and dc and some increment with dc, C plus dc, what is the molecular speed. However, calculating these molecular speed, one should be very careful. Please note that it is assumed that in kinetic theory of gases that the fraction of molecules moving in one particular direction, almost the same number of molecules are moving backward. That means if we try to take the average speed in this way, then velocity being the vector quantity moving in opposite direction, this essentially will give the normal average of these molecules will be 0. Therefore, to avoid this, because more than the direction which are having random, we are more interested in terms of the magnitude. Therefore, what we do that considering the magnitude of these molecules speed, that is magnitude of velocity, that is the speed of these molecules, taking the square and then averaging and taking a square root. In turn, the speed which is obtained is termed as root mean square speed, and which is essentially denoted by Vrms is equal to square root of this the brace which we see that something like this. This is called a time average or ensemble average. That is, by doing this, what we essentially do is that squaring of all the molecules speeds and then adding and then divided by the number of molecules. The n in this equation 1.14 is represented as number of molecules. This kind of the speed which is obtained is called the root mean square speed. That this speed, how to calculate using the Maxwell-Boltzmann distribution. From kinetic theory of gases, it has been said that this Vrms is essentially can be represented as Vrms is equal to square root of ensemble averaging of that molecular speed is equal to the integral of 0 to infinity c square xi c and dc. This speed distribution function is represented as xi. So xi c dc, and then if we have this xi c which is given by the equation number, you can see here that which we have written here 1.13. In this equation, if you insert, that is substitute in this equation, then we come across this expression, that is Vrms is equal to 0 to infinity 4 pi c square m by 2 pi kappa t, where kappa is nothing but the Boltzmann constant, and the value of kappa, the Boltzmann constant, is 1.38 into 10 to the power minus 23 joule Kelvin to the power minus 1, or also you can say joule per Kelvin. That means then again we are multiplying with c square, then this exponential expression and dc. Since 4 pi and then this bracketed term full m by 2 pi kappa t to the power 3 by 2, This is essentially a constant. So taking out of the integral, the expression becomes Vrms is equal to 4 pi in the bracketed term, and then the integral 0 to infinity c to the power 4 e to the power minus m by 2 kt c square dc. This integral is of the following form. That means a standard definite integral property is that 0 to infinity something alpha to the power 4, where alpha is the variable by which you are integrating this the integral exponentially, minus k dash, which is a constant here, alpha square. This turns out to be something like 3 by 8 pi by k dash to the power 5 and in the power 1 by 2. If you use this expression, a definite integral, in our expression 1.16, what we observe finally on solving, we can get Vrms is equal to 3 kt upon m 1.18. Please note that this is a very important expression in kinetic theory of gases. In this way, the translational kinetic energy, that is the molecules which are moving or performing the translational motion, this can be written as E translation is equal to half mvrms square, where Vrms is again the root mean square speed. Then it comes out to be 3 by 2 kt. Please note that this expression tells us that the translational kinetic energy does not depend upon the mass of the molecules. It only depends upon the temperature. When we'll discuss about the kinetic interpretation of temperature, we will again use, so for the time being, we'll move forward for our next speed. That is termed as average speed. Please see here, since we are talking about the average speed, not the average velocity, therefore we are here concerned only with the magnitude of the velocity, that is mod of c. That's what we have represented with mod of c. Now, this is written as V averaging is equal to sigma, that is the addition of all the molecules speed, and then divided by number of molecules n. Now again, using the Maxwell-Boltzmann velocity distribution, this can be evaluated from the gas kinetics. V average is equal to the ensemble average is equal to 0 to infinity c xi c dc. When again you substitute back the xi c, then we can get this something like this expression. That means V average, that is equation number 1.21. What it says, V average is equal to 4 pi in the bracket m by 2 pi kappa t to the power 3 by 2 and then 0 to infinity c cube e to the power minus m by 2 kappa t c square dc. This can be of the following form, something like this, that is 0 to infinity again alpha cube, a standard result of definite integrals, that is exponential minus k dash alpha square d alpha, which can be evaluated as 1 by 2 k dash square. Using this result, the equation 1.21 in our integration, we can get the following results. After doing this solving, then we can get V averages is equal to square root of 8 kappa t upon pi m. This is nothing but your V averages. Now, since we have brought out two speeds, that is the average speed and Vrms, that is root mean square speed, the relationship between these two speeds is approximately Vrms is equal to 1.12 V averaging square. Now, the third one is the most probable speed. What is that? Let us quickly go back on the graph of this. You can see here again in figure 1.11 the effect of temperature on Maxwell-Boltzmann distribution for a certain gas we are talking about. Please note, whatever we are discussing is for an ideal gas based on the kinetic theory postulates. Then we can see let's say this is a black line here. We have denoted the maximum velocity as the most probable velocity. That means though a very less number of or a fraction of molecules have this velocity, but this is the most common velocity observed in the molecules. That means this is the velocity which is in the speed distribution having the maximum probability of having. Since this is, and from the plot, since this is the maximum velocity, therefore using the maxima minima principle of this Maxwell-Boltzmann distribution, we can obtain this most probable velocity that we want to see here. Please see it that since we are aware of the distribution function, we can essentially denote the full size xi, that is a complete expression, in this form: beta c square e to the power minus alpha c square, where alpha, beta are constant, arbitrary constants. They are given as beta is equal to 4 pi m by 2 pi kappa t to the power 3 by 2, and alpha is equal to m by 2 kt. Now, from the maxima minima principle, as I said, if you differentiate this xi with respect to c, we can obtain something like this. That is, you can see that since c square he is also here and in the exponential term, therefore the differentiation will take by differentiation by parts. Doing so, this exercise xi c, where xi dash c denotes the first derivative of xi c with respect to c, that is d xi c upon dc is equal to beta times 2c and then e to the power minus alpha c square plus c square, then minus alpha, that is taking the derivative of exponential term, then here minus alpha c square will lead to you minus 2 alpha c, that's what essentially I have written here, and then e to the power minus alpha c square will remain. Now, equating it to 0 to find out the first derivative to be 0, and then we want to see with respect to that point whichever will be obtained here of the value of c, whether the function xi c will be maximum or minimum according to maxima and minima principle. So let us see that if we solve it, then we can take the e to the power minus alpha c square common, and then there are two terms remains. First is e to the power minus alpha c square, and 1 minus alpha c square is equal to 0. Note that the first term cannot be 0, because even though c is equal to 0, the maximum value, we know that e to the power 0 is nothing but 1. And then, since this cannot be 0, always a positive quantity, therefore the only option left is that we have the 1 minus alpha c square is equal to 0. And then this leads to you an important result, that is called c is equal to 1 by square root of alpha. Substituting back in the second differentiation, likewise we did it here. If you perform a second derivative of xi c again, then you will obtain, and then substituting back this c equal to 1 by square root of alpha, this value, then you will get this like something expression minus 4 beta by e, and you note that since beta is a constant, a positive quantity, e is a constant, a positive quantity, and 4 is a constant, and there is a negative sign. That means after substituting this value, we get the second derivative negative. Obviously, this shows from maxima minima principle that the local point, the curve is having a maximum. That means the most probable speed is nothing but the maximum obtained speed for a particular speed distribution for the constant number of molecules. Now, in turn, the most probable speed, we can see that this can be written as Vmp is equal to, that is subscript as mp, most probable, is equal to square root of 2 kappa t upon m. And now, comparing this with averaging, we can say average speed V average is equal to 1.13 Vmp. That means for a particular speed distribution function, the three molecular speeds is showing the nature something like this. That is, the most probable speed Vmp is lesser than V average, and which is in turn lesser than Vrms, that is root mean squared speed. That means we can see that as we have derived or we have obtained the relationship among the three speeds, and we have evaluated using the same distribution function, that is Maxwell-Boltzmann distribution, we can also obtain the energy distribution function. Interestingly, both the distribution functions are almost alike. Now, let us recap, having a quick review of what we postulated about the gas kinetics, and then we will move on, because our next topic of discussion is, you can see here, theory of molecular collisions and mean free path. Let us define what is the mean free path here. Please understand, let us review that for an ideal gas, we have assumed that the molecules are solid balls, and however, the total volume of the molecules are very, very less, that they are very tiny spheres kind of thing, in comparison to the total volume of the gas contained in the container. That means, if this is the true, we are assuming, then please note that what we are essentially telling, that the gas is very dilute. Second thing we talked about, that the intermolecular interaction between these molecules are almost none, except only when they are colliding with each other on their path, as well as where to the wall of the container where the gas is occupied. Thirdly, what we say, that these molecules are moving in the straight lines and they follow the Newton's law of motion. Moreover, these impact, that is the collision with the wall as well as among themselves, these molecules are having elastic collisions. Elastic collisions means, for this instantaneous collision, that is, the molecules are colliding at very high speed, but they are in touch with each other at very less amount of time, in comparison to the time spent in traveling before and after collision. That means the conversion of kinetic energy of these molecules into the potential energy soon after collision will be recovered back in terms of kinetic energy. That means, essentially, during the elastic collision of the molecule, as per the gas kinetics, the total kinetic energy as well as the momentum remains constant. With this hypothesis, what we say generally, the postulates or assumptions of kinetic theory of gases, that is so far whatever we have evolved, the speed distribution function, energy distribution function, as well as the three speeds, most probable root mean square speed and the average speed, all these are true for dilute gases. In nature, it is not possible. These are these benchmark standard results. For real gases, all these things are not 100% valid. And then we will come across these further some properties which we'll discuss in later. Now look at this thing, that what happens, since the gases, when they interact with each other and when the temperature varies, then from the chemistry point of view, we know that when the gases interact, they form the products. In 1916, the Max Strauss and William Lewis, these were the first two scientists who explained that how the reactants have the interaction with each other and produces the product. Please note that this they tried to explain using the gas kinetics. Therefore, this discussion is particularly valid for the gases phase reactions only. What is said, that the reactants molecules, that is the gas molecules, I will say only the molecules here, we are inherently assuming that these are the gaseous phase only, that these molecules, while having the collision with each other, must have a minimum amount of energy that we have already studied, is called activation energy. And when they have a certain amount of energy, when they are interacting with each other, then only from the reactants the products are formed. Then what we essentially say, that the kinetic theory of gases what we say that in this collision process, when these molecules are colliding with each other, then what is happening, that suppose this molecule is moving in a straight line according to the kinetic theory of gases postulates, it is interacting with this molecule. Then since it is a elastic collision, the reactant molecules are retaining their magnitude, but they change the direction. Further on, this molecules of the reactant, this is going further, and then it is again changing its direction. In turn, what we see here, that between the path of this tagged molecule, let's say this is my A molecule which we are interested in. However, in the fraction of molecules, every molecules are tagged. So let's say if we consider the molecule A, then in the path after collision, this fellow moves here and here. Then the path in between is traveled between the respective or successive collisions are not all same. Therefore, to define the average distance covered by these molecules, we take averaging of these distances covered. By definition, please note that the path traveled in two successive collisions, the averaging of that path is termed as mean free path in the gas kinetics. And this mean free path is usually denoted by lambda. It is given as lambda is equal to 1 upon square root of 2 pi n naught d square, where n naught is the number of molecules per unit volume in cubic meters. It is also termed as number density. And d is the effective diameter of the molecules. We have assumed the perfect spheres. They may be, they may not be. Therefore, we talked about the effective diameter of those molecules, of these different variations, varied diameters. So here, this expression shows that when the diameter is small, that is, the size of the molecule is lower, the mean free path is more. What it says? It says that if the size of the molecules is lower, then the frequency of collision is lesser. Now, this can be again represented if we see that if m is the mass of the molecule and rho is the density of the gas, then n naught can be represented as m by rho. That means it can be written as lambda is equal to m by square root of 2 rho pi d square. Now we can say here that if this, what we said here, that if the size of the molecules are reduced, then collision frequency is automatically decreased. That means larger size molecules are having higher chances of collision, and then they successfully collide and then form the reactants. That is why these two scientists, the Max Schwartz and William Lewis, they told that during the collisions of the gaseous phase, the reactants, all of them are not leading to the products. Only a successful number of collisions which are having the adequate activation energy such that their size as well is adequate, so that the mean free path is required for the reaction to complete should be present. Now, moving on this thing, we can now see that since we have defined the mean free path and we have understood about the collision process which is taking place in the gas kinetics. Now let us derive very important relationship or equation of state for an ideal gas. Let us first see what is the kinetic interpretation of pressure. That means when these molecules are colliding with the wall of the container, how the pressure is defined. Now, for doing this exercise, since a large number of molecules in a particular regime or flow regime which we are interested in, the fluids in motion or fluid lump, we are considering only one molecule, and let's say this molecule is going to collide of this wall. Since we have said it that the molecules are having random walk, That is, at any particular instant where they are starting and there we are observing started observation. However, they are all the time even in this room also the molecules are always in random motion. But any instant, tagged instant, we are interested in observing how the molecules is behaving. So please note that we are not having any preferential direction of motion of the molecules. In the Cartesian coordinate system, this can be said that x, y, and z direction, we are not having any preferential direction. We will take that, let's say, if the molecules are moving in x direction. That means if the wall, which is vertical here, and in the s direction, the unit normal vector is I, is here. Now, we are interested in seeing that the molecules which is having the velocity, total velocity v, x component, that is in s direction, the velocity component is vx. Hence, the linear momentum we can say in the positive x direction is plus mvx. Since again the collision is elastic with the wall, then after the collision, only the direction of the molecule is changing. Let's say, suppose it is something like this. Then in this case, you see that the molecules is just opposite, that is the x component is becomes same magnitude mvx but with a negative sign. But in this case, we are seeing that the change in the momentum in x direction. Therefore, since the other two directions are unaffected, therefore, if we try to write down for a single molecule the change in momentum, then we can say that if v is represented as, let's say, vx, vy, and vz, that is vx, vy, and vz are three components along x, y, and z direction, then v initial we can write down the positive vx, vy, and vz. After the collision, since the velocity component in y and z directions are constant, they do not have any change, they do not experience any change. Therefore, the v final velocity we can express something like minus vx I plus vyz and plus vzk. Therefore, change in linear momentum, we can say that delta p in the vector form, we can say mvf minus mvi. That essentially, if you substitute vf and vi from the equation 1.34 and 1.35, we will obtain this is equal to minus 2 mvx I. That means this is the change in molecules during the collision of with the wall of the molecule. That means the same amount of the momentum transfer will take place to the wall with a positive sign. And that's what delta P wall is written as 2 mvx I. Now, since we have derived it for a single molecule, now but there will be a lot many molecules. So let's say a fraction mole of molecules we are interested in. Therefore, in that case, assume in the second figure here 1.3b, what we are observing that this is a wall, again the same wall, and we are having an imaginary cylinder where many molecules you are seeing in different directions. Some may be going to impact, some may be coming back. Now, let's say the cross-sectional area of this hypothetical cylinder is A. Then we are interested in how many number of molecules are present in this hypothetical cylinder. We are interested in calculating that, and once we calculate, we are near to our results. It is seen that if the total number of molecules is n, then per unit volume, that is the molecules per unit volume for entire gas, can be written as n by v, where v is the volume of the gas. Okay. Now, the volume of this hypothetical cylinder is, we can, if this is a hypothetical cylinder with area A, note that it is impacting here on the wall, then this area is also A, then the molecules which is coming from here, and if the observation time, that is the time interval in which we are observing this process, the collision process, if it is dt, then the distance traveled by this molecule from here and going to colliding with the wall here is nothing but Vx dt. That means the volume will be nothing but if this length is equal to this length. Now the volume of the, let's say, V dash of this hypothetical cylinder will become this L into A, that is Vx dt into area. That's what we have used here, that if the number of molecules per unit volume is n by V, therefore in the hypothetical cylinder, imaginary cylinder, the total number of molecules will be present as, can be written as n by V Vx dt A. But please note here that in the direction in which we are observing, that is in this cylinder, it is termed as that almost a half number of molecules moving in x direction, that is in the positive x direction, then about same number of molecules are also moving in the backward direction. That means in the which we are interested in, the total number of molecules present in hypothetical cylinder in x direction is about 1 by 2 n by V Vx dt into A. If what we have calculated here, delta P was 2 mvx I, that is in x direction, the x component of the linear momentum change, that the momentum transfer to the wall, then we can say this dpx is equal to 2 mvx from here 1.38 1 by 2 n by volume Vx dt into A, which is essentially obtained because 2 and 2 will be cancelled out, and then we get is dpx is equal to mvx square n by V A dt. Now, since the A is the area where the force is exerted, therefore the force can be written as dpx by dt. That means the linear momentum per unit time. Now this is termed as rate of linear momentum per unit time, or rate of the linear momentum change is nothing but your Newton's second law says that is nothing but the applied or impacted force by the molecules on the wall is nothing but fx dpx by dt mvx square n by V A. Now, since the force per unit area we know that is known as pressure, therefore P is equal to Fx by A mvx square n by V. This is an important result, and since now here we will try to make an argument that this Vx, if we replace with the time average or ensemble average of the molecular speed in x direction and writing instead of V as Vx ensemble average square, then we can write down expression again as P is equal to Fx by A m ensemble average Vx square and then n by V. Now, molecular distribution is assumed to be isotropic nature. That is, isotropic property means that there is no preferential direction. The properties remain same in all direction. And then therefore, the average value of this component, that means what essentially we try to say it here is the ensemble average of the speed in x direction. That means if Vx this is equal to the ensemble average in y direction and in z direction, all three components are same. Therefore, if we take the ensemble average square, then we will find it here that this is 3 times Vx square A. That means if we try to obtain here solving this, what we see here, that is this is 1 by 3 times ensemble average total V square. Therefore, using this expression, we obtained the value of Vx square is nothing but 1 by 3 Vrms square. We note that this quantity is also termed as Vrms square. Therefore, the component Vx square can be written as 1 by 3 Vrms square. Now, in such a situation, the pressure given by the equation which we have obtained here 1.43 is that m into ensemble average x square n by V can be replaced using equation number 1.15, and hence we obtain the result as P is equal to m by 3 V RMS square n by V, and hence in the let us take the bracket 1 by 3 out and then mn by V RMS square. Further, since what we here observe that the shape of the container is not coming into the picture. For our convenience, we may take the cube of the fluid lump where we are performing the analysis. However, since the shape is not coming into the picture, only the value depends upon, the pressure depends only upon the volume of the container or the gas which is occupying this container, occupied in the container. Therefore, the shape is immaterial for the pressure. Only the volume does matter. Please note this is a very important result. In such a situation, doing some algebraic manipulation for equation number 1.17, what we observe that P is equal to can be written as 2 by 3 n by V half mv RMS square. That means we are trying to bring down here the equation in the form of kinetic energy, that is, which is given as translational kinetic energy half mv RMS square. Then using this result, what we essentially find it out that since we have already seen for the standard result that E translational results is equal to half m V RMS square can be written as 3 by 2 kappa times T. Using this, we have obtained here, inserting this, what we obtained here, that P times pressure times volume is equal to number of molecules, then kappa, and then T. Furthermore, this is the very important law known as ideal gas law, what we have arrived with. And when we see this n into k, the number of molecules can be given inside this sample of gas, or fraction of molecules. Number of molecules is given as n into Na, where n, small n, denotes the moles, and Na is nothing but Avogadro's number. This n, and we know from the Avogadro's number that 1 mole, the Avogadro has given that 1 mole of the any ideal gas contains 6.023 into 10 to the power 23 molecules for 1 mole of the gas. Therefore, using this expression again, that is 1.51, and substituting back in 1.50, what we essentially get is that P into volume, N into Na, that is K into T, and further noting that the Boltzmann constant and Avogadro's number, this product comes out to be a new constant Ru, which is nothing but the universal gas constant. The value of the universal gas constant is equal to 8.314 joule per Kelvin and per mole, is written as here joule per Kelvin minus 1 and the power mole power minus 1. And therefore, what we essentially find out that PV is equal to nRT, and we are familiar with the results from our school days. Now further, let us go quickly more and review it, that this number of moles we have seen and studied comfortably that n is number of moles can be obtained using the mass of the gas divided by its molecular weight. Therefore, by doing this, inserting this result into 1.53, we obtain PV equal to mRT. Note that here R is specific gas constant. R is specific gas constant, written as specific constant, and given as by substituting Ru by Mw. For air, which is very much important, because all the fluid dynamics or incompressible flow, compressible flow, fluid dynamics, which is a generalized branch of science. For aerospace engineering, our fluid is none other than air, where our aerospace vehicles are flying. Therefore, we are more interested in having the expression for air. Using the 8.314 for the universal gas constant, and the molecular weight of air is something around 28.97. Using this, this gas constant, specific gas constant, the value comes around 287, which we use in the numerical expressions. And therefore, using this, we have obtained here that rewriting this expression, that is the expression number 1.50, again 1.50, that is PV is equal to NKT. Now, when we write down N is equal to PV upon KT, that's what I have written again, an important result here, that N is equal to P times volume upon kappa into T, that is the Boltzmann constant, and then temperature. Please note here that for a certain gas, certain ideal gas, the pressure for a standard or fixed value of pressure and temperature, the number of molecules are totally dependent upon the volume. That means if two gases having the same volume, their number of molecules interacting or mixing with each other are essentially same. This is termed as Avogadro's hypothesis, which is written here. It also says that if two gases are interacting with each other, then their volume at one particular pressure and temperature are always in integral proportion. That means their molecules, number of molecules are also interacting with in the form of integral proportion. That is the molecules from the both sides, that the both gases will always be their numbers in integral proportion. Now, let us see, since we have already defined the expression of translational kinetic energy. These molecules, we have seen that the translational kinetic energy is given by half mvrm square 3 by 2 kappa times T. What we see here, that the kinetic energy here, Vrms, is considered in this that the molecules are moving only translational motion. That means we are not included here the other two motions, that is the rotational as well as the vibrational motion. Therefore, this expression says 3 by 2 kT. An interesting observation from this expression, which we have already derived, can be made. Please note that this translational kinetic energy, if we write in the form 3 by 2 kappa T, then is independent of mass of the gas. That means that kinetic energy solely depends upon the temperature of the gas. That means if the temperature is somehow brought to 0 on Kelvin scale, then essentially the translational kinetic energy will become 0. What it shows that the molecules are now in the frozen state, and hence once they are in frozen state, there will be no pressure involvement, that is the pressure becomes 0. However, the modern concepts have shown that the molecules are never, even the electrons are not having any freezing, that is their movement does not freeze. Therefore, this energy, which is hypothetical energy and then available at t equal to 0, where the electron do not have the 0 energy, that is called as 0 point energy of the molecule of the electrons for a certain gas. Again, rewriting the expression of root mean square speed, that is again rewriting from here this expression translational kinetic energy, and one more observation we can make here, that Vrms is equal to the square root of 3 kappa T upon m. M is the mass of gas, which can again be written as m by Rw. That is, if we remove the k and m from their respective expression, we can again rewrite 3 Ru by T, that is 3 times universal gas constant upon m, where this is mw, which is the molecular weight of the gas. What we see here, that if the mw is small, that is the gas is lighter, that is the molecular weight is lower, that is lighter gases, the RMS speed is very high. And for heavier gases, the RMS speed is low. We have already talked that this speed, where the effect of molecular weight, we have seen in the graph that because of this only, the lighter gases are found in the upper atmosphere, because they have the higher molecular root mean square speed in comparison to the heavier gases, which are found in the below layers of the atmosphere. Now, let us see and discuss about the internal energy. What is an internal energy? By definition, we as instructor must emphasize this fact here. Moreover, from first law of thermodynamics, where we defined something that in a system, when the heat is supplied, then it some portion of that heat applied or supplied to the system of the gas is going to increase its energy, which is called as internal energy, and remaining portion is used in delivering the work by the system or the gas on the outside surrounding. To look something more from the gas kinetics point of view, let us review what is this internal energy. Please note, internal energy from gas kinetic point of view is defined as the energy when the center of mass of the complete molecules under observation is at rest. That means the internal energy can be written as the center of mass of the molecule. That is, if the center of mass is at rest, then what is the kinetic energy at which the molecules are moving? And there is one more component, two more component you can see, that is U inter and U intra. That is, when the molecules are interacting with each other, then what is the potential energy? And furthermore, within a molecule, depending upon its structure, whether it is a monatomic gas, whether it is a diatomic gas, whether it is a triatomic gas or polyatomic gases, what are these components? It has been said that U inter, we can see here that the U inter, we can plot something like this. Let me erase this for some space here. And we have seen from our school physics days that the observation is something like this, that the intermolecular forces which are acting, let's say if this is the intermolecular force, and then with respect to the distance between the molecules which are interacting, let's say if this is the r distance. If we plot this graph, what we have observed, the trend is something like, let's say if this is r naught, which is a particular minimum distance at which the plot is showing different behavior. On this case, what we observe that the force is something looking like is something like this, and then moving like this. The same graph, if we plot, which we are familiar with, energy versus R, then this graph is something shown is like this, where this is here again R naught. Now we see here, this is the minimum point where the graph is changing its slope from left to right, and therefore this point is termed as, in the graph mathematically, point of inflection. That means what it says, that when the two molecules are having a R, and when this R, that is the distance between these two molecules, are decreasing, then when it comes to a minimum distance, this side is the force of repulsion, and this side, right side of this line R naught, is force of attraction. That is, when the molecules are too close, they start repelling each other. However, when the distance between these two molecules are more than R naught, they attract each other. That means at R naught, the energy which is shown here, that is the point of inflection somewhere here where the curve is changing the slope, this essentially represented by the minimum point in the energy here, that at this R naught, the intermolecular interaction, that is the potential energy with intermolecular interaction, U inter, is minimum. Similarly, the U intra comes from the internal structure of the molecule. That means the molecule is composed of atoms, and then these atoms in these molecules also vibrates when you increase the temperature. And during this vibration, they have the both kinetic as well as potential energy. And here, this U intra represents the total potential energy involvement. But please note that in this turn, when this internal structure, when the temperature is lower, let's say room temperature, then intramolecular internal energy does not play into role very much. However, at very high temperature, you must not ignore this thing. At very low temperature, that is the freezing temperature, let's say 0 degree centigrade for water or for other gases, negative temperature, it has been seen that the value of or summation of U inter and U intra is very much negative, larger negative, and Kcm is lower, which makes this summation, whole summation, E internal, that is the internal energy of the fraction of gas becomes almost negative. Because of this reason, at very low temperature, the matter is found either in liquid state or in gaseous state. However, as soon as you are elevating the temperature at higher, that means at very high temperature, all three of them having the larger positive value, making the E internal greater than 0. Hence, the molecules in this case possess sufficient energy to become a gas, and they are free to move wherever they are walled in. Now, after this understanding of internal energy, we should define a very important theorem of gas kinetics known as equipartition of energy, and that in turn define the degrees of freedom. As we have talked about here, let us have a pause and we think what we have discussed so far. We said the molecules which are having the random motion are colliding with each other momentarily, instantaneously, and with each other as well as with the wall, and that is giving microscopically the properties that is the and on the microscopically the properties which can be correlated with macroscopic view. And then since we started microscopically and then we brought about a equation of state PV equal to nRT, that is, that calculates the properties at macroscopic level, however this expression brought out using microscopic. That means both the microscopic point of view and macroscopic point of view are interrelated with each other. Now, what happens? The molecules, since we said that they can perform the three kinds of motion: a translational motion, linear, rotational about the axis, and as well as vibration at their own point where they are located. It is said that any quadratic term, let's say if molecule is performing a translational motion, the energy, the translational kinetic energy, can be written as something like this expression: E translational is equal to 1 by 2 mvx square plus 1 by 2 vy square and 1 by 2 vz square. What we see here, this is a quadratic term